So,
Professor Tiwari, can you hear me?
hello. Hello. Hello, Professor Tiwari. I am audible.
Yes. Yes. Yes.
Okay. So now I can start. So very morning, everyone who are present in today's seminar. So first of all, I would like to warm welcome to our Honorable Vice Chancellor, Mizoram University, Sri KRS Sambasiva Rao, and I would like to welcome Sri HB Srivastava sir, DGTM DRDO New Delhi, and I would like also to welcome Sri Pathak DFTM DRDO New Delhi, and I welcome to Renu Sharmaji and Dr. Kiran Mala, scientist DRDO, in this today seminar, and I heartily welcome to our today speaker, Professor Z.D. Yadav from ICT Mumbai, and he is a distinguished scientist and Padma Shri awardee from Government of India. So, sir, warm welcome in this webinar, and I also like to welcome other uh, guests who are in panel today webinar, and I also welcome to all participants who are connected online in this webinar. So welcome to all, everyone. Again, thank you.
Thank you, Professor Mehta. So may I request DGTM sir, please say a few words. Then
Thank you, Professor Tiwari. I join Professor Mehta in welcoming all of you, all the participants, and especially our Vice Chancellor, sir, and our distinguished speaker today. We have, of course, he'll be introduced a little later, but since I had the opportunity to go through his biodata, a very distinguished, renowned, and accomplished person in the field. And the topic also chosen is I
sir,
got disconnected. Can you hear me now?
Yes, sir. Yes. Now it's okay.
Okay. So, very well chosen topic also, which is of high importance to the country. Hopefully, many researchers and many decision makers and policy makers will get benefited by the talk. So, I look forward to hearing Professor Yadav, and hopefully, we will have the opportunity to work also in future together. So, thank you, Professor Yadav. Thank you, Professor Rao, and thank you, Professor Tiwari and Mehta. Let us move forward in the program.
Okay. Thank you, sir. Thank you, sir. Sir, VC, sir, is it possible, sir? So, yes, sir.
Sir, who is a very renowned scientist in the country in the field of chemistry, chemical technology. I invite him in a meeting at night, so I think he can remember me. It was an opportunity that we wanted to see you in personally in Mizoram University, but because of COVID situation, we could not invite you here. So I thank you very much for joining us today and for gracing the occasion in this program. And we are very eager to listen to you, sir. Thank you.
Thank you, sir. Thank you very much. Despite your tight schedule and traveling, but even then, you are joining is a great pleasure and great for us. So thank you, sir. And as we all know that this is along with the DRDO, we are having Northeast Science and Technology Center in the Mizoram University with the support DRDO, and that we are celebrating. So we are a lecture series, sir, that we are organizing. So this is the lecture from the Northeast Science and Technology Center that we have organized, and we are with us with such a distinguished personality from ICT Mumbai. It's a great pleasure, of course, for me to introduce you, sir. It's a big the biodata. If once we look into that, we see that nothing else left with what he has not touched or what he has not done. So, sir, it's a great pleasure for me to introducing you. Professor G.T. Yadav is one of the topmost highly prolific and the accomplished engineering scientists in India. He is the internationally recognized by many prestigious and rare awards as an academician, researcher, and innovator, including his seminal contribution to education, research, and innovation in green chemistry and engineering, catalysis, chemical engineering, energy in engineering, biotechnology, nanotechnology, and development of clean and green technologies. For more than 10 years, he served as the founding Vice Chancellor and R.T. Modi Distinguished Professor and Tata Chemicals Darbari Seth Distinguished Professor of Leadership and Innovation at the Institute of Chemical Technology, ICT Mumbai, which is deemed to be a university having elite status and center of excellence given by State Assembly on par with IITs, ISCs, ISC, and ISERs. He currently holds the titles of Emeritus Professor of Eminence and J.C. Bose National Fellow in ICT. He serves as the Adjunct Professor at University of Saskatchewan, Canada, RMIT University, Melbourne, Australia, and conjoint Professor, University of Newcastle, Australia. He was conferred Padma Shri, the fourth highest civilian honor by the President of India in 2016 for his outstanding contribution to science and engineering. He has been recipient of 2 honoraries, DSc honorary causa, DYPU, and Chancellor. He created many records at ICT Mumbai. Under his dynamic leadership, ICT made phenomenal progress, having been declared as Category 1 institute, having started 23 new academic programs, 5 new departments, and several centers of excellence, and establishment of 2 off-campuses in Bhubaneswar with total support of IOCL, and Marathwada with total support of Government of Maharashtra, and collected phenomenal funds. The ICT is listed in top 100 institutes in the developing world by Times Higher Education Ranking 2019. The Atal Innovation Ranking of MHRD has placed ICT as #1 among government-funded universities. He has personally won over 125 national and international honors, awards, fellowship, editorship, and several lifetime achievement awards by prestigious industrial organizations. He is an elected fellow of Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences, Indian National Academy of Engineering, as well as the World Academy of Sciences tries to us. He is a fellow of Royal Society of Chemistry, UK, Institution of Chemical Engineers, UK, Indian Institute of Chemical Engineers, Indian Chemical Society, and Indian Society for Technical Education, among others. His research productivity is phenomenal, with supervision of 101. I may be wrong, there may be more numbers. So, and 122, more than 125 master's theses, which is the first record in ICT and for any engineering professor in India. Besides, he has supervised more than 40 postdoctoral fellows, several summer fellows, and researches. He has published more than 100 research papers. Sir, it may be more than that. The recent number is every day it is increasing. So 115 national and PCT patents, 74 granted, 3 books, H-index of 62. Today only I checked through Google, I-10 index of 304, more than 14,000 citations in journals, patents, books, and monographs. He is still actively involved in guiding doctoral students patenting, publishing, consulting, and transferring technologies into industry. The American Chemical Society published FEDSRIF special issue of Industrial and Engineering Chemistry Research 2014 in his honor, with 65 original research papers from scientists from all over the world. He is the founder president, ACS India International Chapter. He is an editorial boards of prestigious journals. It's a huge list. Some of them: ACS Sustainable Chemistry and Engineering, Green Chemistry, Applied Catalysis, a Journal of Molecular Catalysis. The list is very big. So he has been a member or chaired several national and international committees of MHRD, DST, DBT, UGC, AICT, CSIR, the PSAs on green chemistry, the Planning Commission, Pan India SNT Committee, and the Government of Maharashtra Rajiv Gandhi SNT Commission Peers Group. He was Chairman, Research Council, CSIR, CSM, CRI, member of RC of IICT Hyderabad and NIIST Trivandrum. He has served as a chairman, member of selection committees of directors of many CSIR lab. He serves as independent director on 4 renowned public limited companies: Aarti Industries Limited, Godrej Industries, etc., etc. He is also a member of Apex Council of Indian Oil R&D Expert Advisory Committee, ONGC Energy Center, Glaxon India Advisory Board on Process Safety, and Governing Council DBT Indian Oil Energy Center, and member of the DBT Pan IIT Center for Bioenergy. He is chairman of DST's National Expert Advisory Committee on Innovation, Incubation, and Technology Enterprise, member of Advisory and Screening Committee of the Common Research and Technology Development Hubs of DSIR, chairman, PAC of International Programs in Chemical Sciences and Engineering, DST, and chairman Expert Committee Waste Management Technology, DST. He had the honor of addressing 3 convocations of renowned universities. He is fond of literature, etymology, and Sanskrit. The ICT's University Song is written by him. It's a great credit to him. Not only the science, he is doing with the literature as well. So there are 47 video clips, including documentaries on his life on YouTube. So one may access it. So we welcome you, sir. And it's a very relevant talk, as the chairman, the DGTM sir has already mentioned that Atmanirbhar Bharat in energy and environment. He'll be talking on that. That is the net zero goal. So, sir, may I request you kindly deliver your talk, sir.
Thank you, Professor Tiwari. Thank you so much, Professor Rao, Shri Srivastavaji, Professor Mehta, and of course, my dear friend, Professor Diwakar Tiwari. I had the honor of visiting your university in Aizawl several years ago. And so I know, it's a very interesting geography. And so what I'm going to do, I'm going to, since we have the, 75 years celebration of our nation's independence. So let me also give some glimpse, what I'm going to talk. So let me see whether I can present in the, so, okay. Can you see my slides? I hope
yes,
you are
sir.
I hope you are able to see my slides.
Yes, sir.
So, okay. So, dear colleagues, Atmanirbhar Bharat in energy and environment, the net zero goal. I'm going to talk on a very interesting topic in which I'm involved as a researcher, as a technology developer, having several patents in this area. And since this is Azadi Ka Amrit Mahotsav, self-reliant India, let me give you some glimpse. So at the same time, I want to offer my hearty congratulations to Mizoram University for this DRDO center. I'm really pleased to know that the university in last 20 odd years has been really doing well. And so once again, I congratulate all your stakeholders for this wonderful thing. So what was said in the Atmanirbhar Bharat? Atmanirbhar Bharat, we wanted to have an economic boost and something like $5 trillion economy. That is what we want to do. We want to have infrastructure across the country. We want to develop systems which are technology driven, and our demography should be vibrant. And obviously, we have to have full utilization of power and of demand and supply. Can we do that? And I personally believe India can certainly do that. We have a greatest advantage right now because we are a democratic country. And just a few days ago, the Global Innovation Index was announced, and India had jumped 35 places from 81 in 2015 to something like 46 in just 6 years. So what it means that our Indian academia can do it collectively, go higher and higher, and as they say, sky's the limit. So I think our academic world should know that they do have the potential and they must collaborate with industry, like you have been doing in Mizoram University with DRDO support and others. So one of the things which was talked about, the Paris Accord of 2015 or Paris Agreement, many nations of the world came together and they said, we are worried for the global warming. The seasonal cycle has changed. There is drought, there are floods, and cyclones and whatnot. And this was all attributed to carbon dioxide emissions, greenhouse gas. What was also envisaged that time, that the major wealthy nations of the world like USA, China, Russia, Germany, UK, Japan, because they are emitting more carbon dioxide, they should take a lead, develop technology, and maybe give to the developing nations. Now, it doesn't happen, as you know that. So, and that time, the United States did not join this, which was sad. And in the recent election, the United States presidential election, the current president, Joe Biden, make it as his important mandate that net zero. And what is meant by this net zero? The net zero that we should have technological advances such that by 2050, the carbon dioxide emissions, net emissions will become zero. So this is what it is, net zero. And this was announced in the summit. This was on April 22nd, 23rd, if I'm not mistaken. And see here, we are lying here at number 7 position, our CO2 emissions. Look at United States is 8 times more than us. Then China and all, and these are all developed nations. And China was supposed to be a developing nation, but look, their industrialization is so much that carbon dioxide emissions are related to industrialization. So what happened in the year 2020, let us look this as a standard reference year. We had CO2 concentrations of 410 ppm. And thereafter in March, we had a lockdown. So practically for the entire year, we did not have substantial economic activity. So somebody will think that, well, the CO2 emissions could have remained steady or, something else would have happened. However, in in April of this year, these emissions increased by 2 ppm. So it is 412 ppm. So what it means, typically, the world uses something like 97.5 million barrels per day of crude oil. The refineries are processing that. During that particular period, and to be, precise, on 10th April 2020, the crude oil price became negative. What is the meaning of that? That means there was more production of crude oil than the storage. So you have to pay for storage. That is what it means. So in the Paris Agreement of 2015, the nations of the world said, can we cut down our emissions and do not allow the temperature rise to beyond 2 degrees C? And to be specific, 1.5 degrees C. However, about a month ago, there was a report. What that report said that by 2030, we already would have reached that temperature. That is very, very dangerous. And if there is no technological interventions, we go on using the fossil fuels, then obviously the temperature at the current rate will go to something like, it will go beyond 6 degrees by the year in 2200. So that will be disaster, catastrophic effect. The world will sink, I can tell you that. So what is the reason? The reason is because our entire economy is carbon-based economy. And what are the carbon sources? Yes, we have non-renewable or the fossil carbon, we have oil and natural gas and coal. And we know that, coal was a major source of power, and still it is a source of power, and it was also a source of chemicals. And after the introduction of oil, and so I'm going to give a little bit of historical perspective, and we will also get new oil and gas finds. And so what is happening these days, they are planning variable capacities refineries. Now the refinery's original job was to create fuels, get fuel so that your vehicles can run, right? Now they are talking about crude to chemicals, even clean chem technologies, a coal to liquid, coal to gas. Like suppose you go from coal to syngas, and clean coal technology and syngas can be used to make many chemicals and materials. On the contrary, when we do not have any carbon source left, we have to depend on renewable carbon, that is biomass. And this biomass can be converted either chemically, biochemically, or thermochemically into variety of products. And this is well known, whether it is fermentation or enzymatic reactions of biomass to gas, and all those things are well known. Exactly a year ago, I published a paper. This is on the production of fuels and chemicals in the world, critical analysis of choice between crude oil and biogas vis-a-vis sustainability and the environment. This paper became highly popular. In fact, we got many requests. They could download it. But at the same time, this was the request from planners in Canada and USA. They found this paper was very interesting. And this is where we have argued about many things. And we have done the economic analysis of this crude oil business, gas and hydrogen and whatnot. So we have been propagating. I have written many articles on hydrogen, including some will still appear in newspapers, in magazines, editorials. And I say hydrogen will be the savior of the world. In our culture, we have a savior, right? Trata, it is called in Sanskrit. So we have a savior, and my personal belief is that hydrogen will be the savior of the world. And why so? And I'm going to talk about this because I'm involved with working on hydrogen. So what is happening, whether the carbon is coming from fossil fuels or biofuels, if there is ultimately the fate of the carbon is carbon dioxide. And if we do not stop this carbon dioxide emissions, sequester that carbon dioxide, convert that into fuels, chemicals, and materials, that objective, the grand objective of Paris Agreement will not be achieved, and we will have problems. And why hydrogen? Because hydrogen is the cleanest fuel, which can be produced from a variety of sources. Typically, hydrocarbons are from water and can be used to convert carbon dioxide into useful products. So the so-called hydrogen, I will talk about that also a little bit later. We can use it for treating biomass, including waste plastic. And since we know hydrocarbons can be reformed into hydrogen, but at the same time, carbon dioxide need to be utilized. So let me give you a little bit of historical perspective. So anyway, in the petroleum-based economy, so I will tell you what happened with the petroleum-based economy and the biomass economy. As I told you, that carbon dioxide is the end result of these fuels. So unless you capture carbon dioxide and valorize it, we will not have the net zero goal. And that is what we want to do. And it is believed by 2054, we will not have any crude oil by the current method of excavation of this crude oil from Mother Earth, because the technology will be very expensive and everything is techno-economical, isn't it? So what do we do? At the same time, because of this COVID, we had many problems. Before the COVID outbreak, there was a price war between Saudi Arabia and Russia. And that has affected the crude oil price, and it went down. That affected the so-called Brent spot price. Then there was a negative price, as I told you, on 10th April. And then it's recovered. And what these pundits say, that unless the crude oil price is something like $45 per barrel, the industry will not be viable. Industry will not sustain this. And to be honestly talking about $60 will be a comfortable figure. Now this is gone to something like 70. All right. At the same time, what happened in the country like USA? USA, they have a cracking industry. And the 7 major companies in Texas, they cut down their budgets to the ridiculous low prices. And that budget was $7.6 billion. It affects economy. And remember, our consumption, as I mentioned before, is something like 97.4 million barrels per day. During last year, April, May, that had come down to something like 85 million barrels. But still, that is a substantial quantity. It will go exceed 100. So why it is so? One of the reasons is that when we have a crude oil-based refinery, do you look at this? The crude oil-based economy, you have to have a distillation and you have all these processes. I won't go into the details of this, but I deliberately incorporated hydrogen here. There are 7 different processes which require hydrogen even in the current refinery to valorize that, go to the higher products. And where are they getting that hydrogen from? They are getting from the steam reforming of natural gas. So this is hydrogen and carbon dioxide. So this is called gray hydrogen. And this hydrogen they are using, and this hydrogen is typically $2 per kg. That is economical. At the same time, as I will show you later, even if we switch from this non-renewable resources to renewable resources and have a biomass as a feedstock, many things are there. I won't go into the detail, but what I can tell you that hydrogen and oxygen are going to be the major sources for conversion of this biomass into useful chemicals and material. So whether you employ the sugar platform or you use the syngas platform and go to Fischer-Tropsch synthesis, everything depends on hydrogen. So what about hydrogen production? And remember, these are the major processes in refineries, like catalytic cracking, hydrotreating, hydrocracking, catalytic reforming, hydrodesulfurization, hydrodenitrogenation, and hydrodeoxygenation. These are the processes which use hydrogen. So that means currently also we are using hydrogen. So since, I mentioned to you that due to ppm increase, we have to, decarbonize this industry. At the same time, should biomass be used as a source of energy? That is what there is an emphasis. And I'm going to argue with you and tell you that that is not a good idea. And why so? So I will tell you. So biomass should not be used as a fuels and chemicals. Right now, our policy to have bioethanol to be blended with petrol and diesel. Yes, we want to increase that. Yes, so it is a carbon neutral process, we say, yes. But if you want to bring down the temperature to less than 1.5 degrees C, the hydrogen has to be used, and that must form something like 25% of the energy mix. So that is the only way we can have this net zero economy. So let us look at the carbon-based fuel economy. So you know this. I have deliberately added this slide because you know that we start with petroleum, natural gas, air and sulfur, and then we produce a variety of a galaxy of spectrum of chemicals through the commodities, secondary, tertiary, intermediates, and finished products. The average general person or the common public only knows about the end uses like textiles, food, transport, housing, recreation, communication, all those things. And our Atmanirbhar Bharat says that we should be self-sufficient. And so many of these things are imported. Look, I remember something like 80% of the APIs are imported from China. We can definitely ban, the apps because you're playing with the electrons. But it is difficult to ban materials which are a source, that the feedstock for your industry. So unless we develop this feedstock here, develop precursors to our industry in APIs, we'll have to continue to import something from China or any other countries, maybe Vietnam and other, South American countries. However, India can make all these things and should not depend on China. And the government stand is absolutely right. So let me take you back. So how do we contain the temperature to less than 1.5 degrees C, and how do we decarbonize the industry? Remember, the carbon in the earth crust is only 0.18%. Maximum is oxygen followed by silicon. Okay, so carbon is not great. However, if you look at the energy transition of this, the energy transition from the energy transition, in 2020, the world emitted something like 25 gigatons of carbon dioxide. And our grand objective of net zero by 2050 is to have temperature below 1.5 degrees C. That means we have to decarbonize. That means we have to stop emitting carbon dioxide in the atmosphere. And that has to come to less than 10 gigatons of CO2. Remember, we had an initial goal of 2 degrees, which will be something like 17, 18 gigatons, and below 10 will be 1.5 degrees C. So this net zero objective, that means either we rapidly transition to that, or we have a business as usual. And so the 2 degree IPCC panel and 1.5 degree, these are the the estimates about the carbon dioxide emissions. In other words, what it means that if you go for our energy and depend on renewables, which will include wind, solar, geothermal, biomass, biomethane, biofuels, I'm very glad that our solar and wind capacities are increasing, and we will have a lot of production of this renewable energy, including geothermal. Even ONGC has geothermal wells in Ladakh and all. So yes, this bio-based economy and the renewable economy, yes, and in this case, the large-scale hydros are excluded, and you see that this increase of renewables will go substantially up to something like 60%. Supposing we take base as 2080 rather, by 2050, this will increase. And so the share of fossil fuels in the primary energy source has to go down rapidly to get the net zero goal. So if you see from 1900, when this petroleum was available to the world, we see that the coal usage is going down. However, even in 2050, some of the things will be still based on coal. So at the same time, the renewable is increasing. Okay, the natural gas is increasing, and the other non-fossil fuels, that is solar, wind, etc., that will be increasing. And so the oil consumption, which is from say 97.4, it should go down substantially in the net zero. And that has to go down to something like 22 million barrels per day. So what it means that our current refineries have to be converted to biorefineries or things like that. And so because of this change in the scenario for the energy demand based on fossil fuels, you see at the passenger car, trucks and buses, aviation and marine, and the non-transport. In the net zero, you see the non-transport is still hard. Buildings and heating of the buildings requires a lot of energy in the Western world. So obviously, we'll have this transition. At the same time, many times the natural consumption is taken, a little bit nearly like the natural gas consumption. So obviously, in net zero, that consumption will go down as well. So the natural gas is a source of near zero carbon energy, where we have three different scenarios. One is a rapid, then we have a net zero. In net zero, when we abate these carbon dioxide emissions, and when there is no one, that is a gray. You see that means this percentage is going up. So carbon capture and utilization is one of the key parameters for this. So here what is going to happen, we have blue hydrogen in this net zero, where they use biomass and they convert that carbon dioxide in something that is called blue. So let me look at that. So if we look at the renewable energy used in power sector, see net zero, you see that the wind and solar, their percentage is increasing rapidly, and the geothermal and biomass. So you see the cost of this wind and solar energy power is going down substantially. And that is good news, because that is what we want. So in the bioenergy in rapid and net zero, you see that we have hydrogen, which is shown here in the net zero. So, and then you have power, then the buildings, industry, transport, biomethane, biomass. So this is what it is. So this is by type. So we see that we have to have hydrogen production, and that is what is required. So when we increase the wind and solar capacity, our dependence of these carbon-based fuels will go down, and that is aimed at. So how do we do that? So carbon can be converted, this carbon dioxide, into chemicals and materials by using hydrogen. So there are three types of hydrogen. One is called green hydrogen, where you use electrolysis of water, where you have clean electricity from wind, solar, hydro, and nuclear energy. That has a zero GHG emissions. This is a gold standard. With reference to that, we have blue hydrogen, where you have steam reforming of biomass, bio oil, natural gas, etc., where the carbon dioxide has to be captured. So even if you capture 90% of the carbon dioxide, having low to moderate carbon intensity, and gray hydrogen, which what the refineries are doing, and I showed you about that. So steam reforming of fossil fuels, it can be anything. It could be naphtha, it could be coal, it could be natural gas, where the carbon dioxide is not taken care of. So the consumption of production of hydrogen, if you look at this, so you see the net zero economy tells us that hydrogen will have substantial usages in industry, then building, in transport and power. And so we have gray hydrogen that will vanish by 2050. So it will be only green hydrogen and blue hydrogen, where carbon dioxide capture and utilization is done. And this information, I have given this reference in my article, but this is based on European Union, the International Hydrogen Council, and Bloomberg, net new energy funding. So you see the hydrogen growth will be from 2% in 2018 to something like 13 to 24%, depending on that particular geography, by 2050. And that means the average compounded aggregated growth rate will be 8%, and there will be something like $150 billion US investment by 2030. So what it means for hydrogen economy, I wrote the articles, I told you that government of India should adopt hydrogen economy. Why? There is a reason for that, and you have done calculations to show so. So hydrogen must be produced cheaply and in eco-friendly manner, and it should serve as the commercial fuel that would provide a substantial portion of the country's energy demand and services. Then in that net zero economy, green hydrogen will play a dominant role. So see, when our energy requirement goes up, the population goes up, we have a dual problem. That is, we want more energy but less carbon, and that is what less carbon. That is what is expected, and that should happen by 2040. That is what we see. And in that, by 2050, about 73% of the share of the energy will come from renewable. And that measure will be solar, wind, hydro, gas, coals will be still used, right? And this is where what we want to do is, so the renewable share will be something like 27% to 51% by 2035 to 73% by, which is about 49,000 terawatt hour. Okay, so green hydrogen, we have, it is a source of fuel as well as energy carrier and storage. There are numerous potential applications, but I'm going to give that in a little while. And there is no carbon dioxide. So we have a very clean source. So what happened in the past? Actually, I want to tell you something about that also. When there was no petrol or crude oil, excavation, what was done in the North America? They were capturing wells. And these wells were then converted, the blubber of the well was used for having oil lamps and making soap. And they were called oileries, okay, the word oileries. Okay, this is a picture which I've taken, and this is some sort of crude refinery for this oilery. And you see, this is the sample, okay. So when we wrote our article, we said, let us trace the historical happenings in this. So we have 1869, I've enlarged this. That was the birth of oil industry, and Colonel Edwin Drake, he drilled the first well in Pennsylvania. And as the rest is said history, you see that the production grew slowly. What was done? Actually, that time there was no use for petrol, only so kerosene. So gasoline was sent into a river or streams. However, we must thank Henry Ford. He introduced the automobile in about 1907, and this petrol or the gasoline found use. And so in the World War I, and particularly in World War II, the technology for the refineries increased substantially. Okay, the refineries started becoming complex. So they become catalytic cracking instead of thermal cracking. And the value of they call it as a spread. Okay, so the spread of this oil spread increased when we wanted to have better technology, whether it is platforming, and because hydrogenation requires this precious metals as catalysts. So very interestingly, you will see that in 1930s there was a substantial growth. You have thermal recovery, then you have silica alumina catalyst, then clays as catalyst, then then zeolites, then ultra stable zeolites, which is used by everybody nowadays. So there was a substantial surge in production. The people became wealthy, and all other industries depended on this crude oil source, right? And so as time went by, the complexity of this industry also increased. It became highly science-based, and catalytic technologies played a very, very important role in this. So you see, and again, as against this, now when we run out of crude oil, if you want to make products which are required by the chemical and allied industry, suppose we say biorefining, which is where biomass is used as a source, we can produce a gamut of chemicals, okay? And these are chemicals, okay, which can be used as subsequently to make many other chemicals. So supposing we want to have, say, biorefining, I mentioned about this crack spread. What is that crack spread? That means if you have $1 barrel of crude oil, how much, and suppose it costs $10, can you make $20 after refining? So that is crack spread, or $30. That means you have to valorize the subsequent products of the refinery. So what we said, suppose we have biorefining where biomass is used, will there, see, this data were available from Department of Atomic Energy. So we use their data in 2020. So they have a fine network. There is a network for transporting. We do not have that network. So we saw that we can look at the crude oil versus biomass. So crude oil, if you get 1 kg, I get 32 megajoules of fuel and 0.2 kg chemicals. But suppose I want to have equivalent thing by using this biomass, 1 kg, I get only 6 megajoule, almost 20%. Or instead of that, we can get 0.8 kg chemicals and material. So what it says that the energy and material balance shows us that this biomass is better suited as a material for making or feedstock for making chemicals and materials, maybe polymers and whatnot. So my thesis is what? That we should not use biomass for fuels. Yes, we can convert. You can have blue economy. You can have blue hydrogen coming from that, but biomass should not be used. So typically, based on that 97, plus 0.4 million barrels per day, that is something like 215 barrels per second. If we want to process this, supposing I take 100%, ethanol, this biomass, I only convert 10 into a fuel per second. But if I convert all 100% biomass into chemicals and materials, then I get 320 barrels per second. So you can see that it is better to convert biomass into chemicals rather than converting to fuels, because simple calculations show that this we are showed in our paper. So then we also looked at the investment of the US Department of Energy for biofuels, because our government of India and Department of Biotechnology has spent a lot of money on biofuels, and rightly so. And many companies are investing in that. But however, when we looked at the DOE data, there are more failures than successes on biofuels. Okay. And there are quite a few on pilot scale. And so you see the size of investment, it is very, very high in the size of investment in this. At the same time, some of these chemicals like, transportation fuel, vinyl acetate, butadiene, styrene, etc., these are basic chemicals which are required. And ethylene and propylene account for the largest, and in comparison with that, I've shown is bagasse. So they have the largest share of petrochemicals because they are required as a feedstock. So what we did, can we look at methane, because methane is a natural gas, or carbon dioxide can be converted into methane, for instance. So that methane to olefin processes or oxidative coupling of methane are major reactions. So these are catalytic processes. And the bubble size in this particular slide shows the current capital cost and processing capacity, which I mentioned in the previous slide, 12,000 barrels per day. See, the thermal efficiency with the steam reforming getting hydrogen, okay, it is 80%. Carbon efficiency 0, but you look at methanol so what it means that the steam cracking of ethane and all. So we see that methanol, we have an investment of 0.6 billion. Methanol to methane to oxidate, olefins is 1.5 billion. So this also tells us that we can look at carbon sources and find out what will happen. And one of the things our Niti Aayog is talking about is methanol economy. In fact, I must tell you, I'm very happy to tell you that my paper on methanol economy in green chemistry had just appeared. Right now I'm correcting the proofs online. So we had argued about what is methanol economy and what's its contribution to net zero. So you see that even if you have methanol, which may come from right now also, they are saying, okay, why not have clean clone processing and go to methanol. And once you have methanol, you can produce all these chemicals. And these chemicals can be used for making many other chemicals. So yes, methanol economy is based on that. So what we said, the cost of electricity is very important for any of these processes, including electrolysis. So the levelized cost of electricity, which is generated by combined cycle power plants fueled by natural gas, is substantially lower than the power plants that either consume biomass or employ gas turbines. So the extremities of this bar represent the minimum and maximum cost, whereas the break-even point is given by this vertical line. Okay, so you see the levelized cost of electricity when you have the natural gas with advanced combined cycle is very low when you use this advanced cycle, and this is per megawatt hour. And look at the other portion of the biomass. So biomass we can convert into variety of value-added products. So you have C5C6 sugars or cellulose, hemicellulose, and lignin. So you see the lignin-based processes, and this is C5C6-based processes. All these are catalytic processes, whether acid catalyzed, base catalyzed, metal catalyzed, or enzymatic catalyzed, all sorts of things. And many of these are oxidation and hydrogenolysis. So that means what? That hydrogen is going to play a very important role. So we have hemicellulose, cellulose, and lignin, and we have important products which are feedstock like our benzene, toluene, xylene, and the butanes in our refineries to xylitol, furpilol, sorbitol, livolinic acid, lactic acid, succinic acid, ferulic acid, name it. So these products can be made, and the carbon dioxide refinery which I'm talking about. So one is nature is doing that photosynthesis. With the help of water, you can get oxygenates and then you convert it into chemicals and fuels, or you take carbon dioxide, hydrogenate it, you convert to hydrocarbons, or you convert to methanol, dimethyl ether, and formic acid. So hydrogen is a key. And similarly, if you look at waste plastics, I won't go into the details, but I want to give a theme like PET or HDPE, PVC, polypropylene, polystyrene, name it. All these plastics can be converted so-called chemical recycling, upcycling, downcycling, all those things can be done by using hydrogen. So this is the waste plastic chemical recycling. So we have chemolysis, pyrolysis, gasification, or hydrothermal processing. See what is happening. In chemolysis, we have hydrolysis, glycolysis, aminolysis, alcoholysis, acidolysis. So instead of burning, you can do this, okay? And so products of pyrolysis are poor fuel oil. Therefore, the product has to be hydrogenated. And they are environmentally hazardous. So yes, so you can overcome this problem by cracking with hydrogen at 100 atmospheric pressure. So yes, hydrogenation of plastic, waste plastic in particular, can also handle these molecules like atoms like chlorine, nitrogen, oxygen, sulfur, which are there in all sorts of this plastic, like whether it is PVC and all. So yes, and these reactions, hydrococking, HDS, HDN, dehydrochlorination, these are handled by a refinery, and they are using this dual function catalyst. That means this technology is available. Why not use this technology to make value added chemical processing of this waste plastic? The answer is yes. So we have PVC, PET, polyamides, rubber, and HCl, water, ammonia, and sulfur, hydrogen sulfide. These are handled by refineries very well. So it is well known. So whether this sulfur, class process or super class process, you get sulfur, and that sulfur will be again useful raw material, right? So what it means, we require better catalysts and new materials by using this processing. And this is where we talk about waste minimization and process intensification. Coming back to India, I want to tell you that by scenario by 2040, 42% of this energy will be made through coal. That means coal will be used, and this coal means there will be CO2 emissions. And this will be actually it will double by 2040. So that means we have to live with our commitment to Paris Agreement, and we have to cut down CO2. And also by 2040 rather, we will have 150% growth in primary energy consumption. And 58% of share of coal will be still in the power generation mix. So we have to go for energy through, solar and wind. Okay, and we have to cut down CO2, which will be double, I mentioned. And look at the renewable energy consumption. This will be something like 20 million ton of oil equivalent today, which will be about 300 million ton oil equivalent. And this will, still coal will continue to dominate. Okay, so we must have carbon negative fuel, and that is hydrogen as the source of energy. I would not go on singing the ballads of hydrogen, but hydrogen is the cleanest fuel. I'll know that. And this particular slide tells you what hydrogen can do to our economy, because I'm talking about benefits of hydrogen economy. So hydrogen can be used as a fuel for transportation. The only issue is that how do you compress it, what sort of material will be required, and how to do it. And these they talk about, ammonia as a source of hydrogen. So you do ammonia splitting, and so you have clean hydrogen, which ammonia can be stored at much lower pressure. Our carbon dioxide conversion to synthetic fuels, our upgrading of oil and biomass hydrogen, ammonia, so-called green ammonia, and fertilizer industry. Then metal, steel industry emits maximum carbon dioxide. So there you should use hydrogen. Then again, chemical and industrial processes, heat distribution. And remember all these things, whether you are renewable, nuclear, fossil fuel, all these things, whatever may be the source of your hydrogen, and that hydrogen can be used for example, fuel cells and generating, electricity. So you can have electricity generated by this. So obviously, the hydrogen potential market by 2050 in exajoules, you see that your power, transport, industrial energy, building, and industrial feedstock. And the bubble size indicates the hydrogen potential in 2050. And so you see, we will have refining, we have ammonia, methylene, and all these forklifts and whatever, which will be used. So the hydrogen demand will increase by 10-fold by 2050. And the areas where it will be used will be power generation, transportation, industrial energy, building, new feedstock, carbon capture, and also existing feedstock. So, and if you look at biomass, I had already told you that hydrogen will play a very important role. Whether you combust, gasify, pyrolyze, or liquefy, hydrogen will play a very important role. When you have a lignocellulosic biomass, you do hydrolysis, maybe alkaline or acid, or maybe ionic liquid. You have to do pre-treatment, and then you produce all these building blocks, right? And so you see that one of the, like benzene, toluene, zoline, 5-hydroxymethyl-furfural, 5-HMF is a important precursor. It is a platform molecule, and all these chemicals based on biomass are very highly, expensive but good feedstock for a variety of industries. So you make money on this, whether it is 2-methylfuran or dimethylfuran or whatever. So 5-HMF, we have done a lot of work in our laboratory. I won't go into the details, but I just want to tell you that HMF is very important. In the biodiesel sector, Glycerol is a co-product. This is 10%. So that can be converted to esters, epichlorohydrin, acrolein, acrylic acid, polyethylates, propanediol, 1,2, 1,3, and all these animal stuff are biotechnology. Look, all sorts of things based on glycerol. So we can do that. So yes, from lignin, we have a variety of products. These are high-value products, syringeol, we know vanillin and whatnot. So we, in the case of biomass, we depolymerize, we have carbon-carbon bond formation, we have selective oxidation, selective hydrogenation, hydrogenolysis, all sorts of things will be done. And so including the current thing where in the fatty oil industry, you have oleic acid, linoleic oil, all those can be valorized. Yes, so hemicellulose, lignin, and fats and oils, all of these will be valorized into a variety of chemicals. And in the case of the so-called green steel, because I mentioned to you, steel is the polluting industry, and they are talking about green steel. So where hydrogen will play a very important role, okay? That is what I'm talking about. And so there is a continuous improvement in the entire value chain when you want to have zero carbon production, for example, electrolysis of water. So this is all energy consuming, right? So if you produce hydrogen, it has to be stored. You require a proper storage. And then you have to need, if you use it as a fuel, you must have hydrogen refueling stations. You have to worry, then you can go to fuel cell passenger vehicles. You again fuel cells. So fuel cells will play a very important role in this. And in the industrial hydrogen production right now, steam reforming of natural gas is 48%, oil naphtha 30%, coal gasification, water electrolysis, and others. In my lab, we did a lot of work on steam reforming of bio-based feedstock and CO2. We have got several patents and written several articles. And these include ethanol, methanol, N-butanol, ethylene glycol, glycerol, and waste biomass. So for example, this is hydrogen production for ethanol. So somebody is interested in this technology. So we are trying to sell our technology. We are also written of steam reforming of methanol for hydrogen production, or the dry reforming of methane with CO2 get to syngas. And once you make syngas, you can produce all sorts of things. So this, my work was supported by ONGC. So ONGC is the energy center. So when we developed this process, we called it, ICT Mumbai OEC hydrogen production technology. This technology can produce hydrogen at less than $1. This is the cheapest in the entire world. When about 10 days back, I spoke in the conference which was arranged by Dr. J.P. Gupta, who is in the Ministry of Environment. I showed that how our technology is superior to many other technologies. And this does not have any carbon. And why hydrogen? Also, this is a general slide. When the housewife burns wood, look at the kilojoule per gram. And when you have hydrogen, look at the specific energy. Hydrogen has the highest without any carbon being in that. So we have renewable energy, we have coal, you have nuclear, and all these direct solar. People are talking about direct solar, direct water splitting, or electricity for electrolysis. And really speaking, our problem with electricity is it is very expensive. So the cost of hydrogen, increases because of electricity. So, and this is coal, oil, natural gas. We know that, but here we have to do carbon sequestration. So obviously, the ICT blue hydrogen processes, which I develop in my lab along with my students, these are some of the references. So let us analyze the source, hydrogen production, like natural gas, wind, solar, uranium. See, in this particular case, wherever there is a carbon with the hydrogen source, you have to do carbon sequestration. In the case of uranium, you have to do nuclear waste disposal. And you may have thermal dissociation to solar thermal sources. So hydrogen production, we have natural gas, the 95%, biomass gasification, you have electrolytic, PM electrolyzer, for instance, or photolytic. And in photolytic, biohydrogen production, we have fermentation and biophotolysis. So you have, these are all, a lot of work has been done and published in reputed journals by many others. So in the solar hydrogen, you can see that what I was talking about. Still also the carbon dioxide is methanol, so methanol-based technology, gasoline, hydrocarbons, or you have nitrogen, so you so-called green ammonia, and then chemicals. So this is what is happening. So industrial hydrogen production, if you compare the reforming technology, steam reforming is the highest maximum use technology, then autothermal and fossil. So in our case, we also work ONGC had given us two problems initially. They had given us copper coke, which they said you develop this, and sulfur iodine. We had worked on sulfur iodine. This sulfur iodine is done by IIT Delhi, but we have done copper cleaving cycle. And we have proved that, the technology maturity, see that steam reforming partial oxidation is a commercial, biogas, biomass gasification is commercial, electrolyzer is commercial. So that means there are two types, the mature technologies and future technologies. So our work falls in this. So what we did, we compared our data with the published information in the literature, including patents. Remember, wherever there is a carbon is a companion of the source for hydrogen, the carbon sequestration and utilization has to be done, CCC. So here, the cost is without carbon capture. You see, this is about $2.27. And then you look at the capital investment, $226 million. So like methane pyrolysis, biomass, direct biophotolysis with algae and all, and dark fermentation. So what it means, these sources have carbon. Okay, so so this has to be taken care of, right? So and then we have photofermentation, solar PV electrolysis. See, the solar PV electrolysis cost is nothing like anywhere up to $23 per kg, very expensive. You cannot have it. So it has to be brought down. So when we did our analysis, we found that we can produce it at 95 cents. Now it is a shocker to everybody. In fact, I got so many inquiries. How did you get 95 cents? So I can tell you that. So that we also did the well to get emission analysis. Of course, the green hydrogen has zero, greenhouse gas emission. Steam reforming of natural gas, 9 kg CO2 per kg of hydrogen. When you have a natural gas with carbon capture and storage in 90%, but it will be 1 and 4. And this is dependent on the prices. So European Union has given this analysis. They say that something like $26.8 per megawatt hour, and the electricity cost is in between this $42 to $106 per megawatt hour, and the capacity cost will be about $730 per kilowatt hour. So what happens with the cost of hydrogen? Suppose, and that was the point of discussion in the panel where I participated last week. That is, electrolyzer cost. The European Union and the International Hydrogen Council says that it is about $1,100, and it will go down to $550, and then it may become $220. In the debate that day, they said, some experts said that they cannot make it less than $1,500. Somebody said they can make it $150. So, and the cost of carbon capture and storage, that increases. And if you want to use steam reforming of natural gas, so it will be $990, something like $1,850. And so what it means, the green hydrogen, what they say, including the US Department of Energy, if you could bring down the cost to something like 1.3 to 2.9, you have achieved. And I'm saying we can do it at 95 cents. And remember, hydrogen, 1 kg of hydrogen gives 8 kg of oxygen. And oxygen, international price of oxygen on a big tonnage basis is 10 cents per kg. That means you can get 80 cents of valorization of oxygen without talking of the hydrogen part. So even if there is a price upside somewhere, still you can make this hydrogen production less than $1.5 per kg. I'm saying 95 cents, right? And what is the US Department of Energy is saying? They said that small plants, it is about $4. Large plant, it will go to $3. And in future, it should be less than $2. And that is when the hydrogen economy will become a reality. So that is likely to happen by 2030. And I'm saying right now, we can do it in India. I see self-reliant, Atmanirbhar Bharat, we can do it. I can do it through my ICT technology. And this is a picture of my technologies, what we did. So we are using solar power. We are using molten salt. We have got patents. Then our copper chlorine cycle, where high water is the input, we get hydrogen and oxygen. And we have CO2 can be also carbonized to methanation to get carbon, methane, and then higher hydrocarbons. Or you take waste biomass, or are you oxidation? You see all these chemicals, hydrocarbon, methanol, dimethyl ether, formic acid, syngas, green ammonia, fuel cells, hydrogen, electricity, all these things are possible, and we can meet the Paris Agreement. So yes, So that is what we want to do. So our ideal goal is to contain climate change, and our effort is in that direction. I cannot say mine is the only one, but modestly I can say yes, we can do it. So that is the existing hydrogen application like steel, ammonia, methanol, that will be extended to regional trains, taxi fleet, blending, name it. And hydrogen is already been blended with CNG, right? That's what IOC did in Delhi. So it can go to transportation and heat and power and name it. That is going to happen. So the production of green hydrogen and net zero goal, the potential of my technology, ICD OAC process, was explained to you. So obviously, this emission of CO2 can be contained by using green hydrogen. So ultimately, we talk about the linear versus circular economy. In linear economy, we pollute the land, water, or air. And with the help of hydrogen, we can become part of this circular economy. And that is what I showed you through my lecture. So of course, we can make new materials, chemicals, and whatnot. We can reuse some of the, bio-based materials. Okay, that we can do. So finally, to conclude, the notion that biomass per se can replace oil as a feedstock for fuel and chemical, we analyze it critically. And I published it. And that was analyzed from economic and environmental viewpoints. So biomass, unfortunately, chemically and geographically incompatible with the existing refining pipeline infrastructure. That means we have to develop that. Biomass is highly light. It has to be, pelletized and brought into densified. So biomass can be used only for production of valuable chemicals and materials and not as a source of fuel that I showed you. And I argued as a lawyer. And using crude oil, biomass shale for the time being, because we do have those sources, the shale gas and biomass, and we can have a combined mix so that the economy doesn't get it, that other economy gets a boost, and we can have, at the same time, we can produce methanol, and methanol-based economy can also be a part of it. So hydrogen economy can be elegantly intertwined to make many chemicals from waste carbon, including waste plastic. So my argument at the end is government of India should adopt hydrogen economy to meet the demands of Paris Agreement. That is the only way we can do it. And what I'm saying, since we are talking about Atmanirbhar Bharat, we can do it. So ladies and gentlemen, thank you so much. I told you the story, success story, what we have been doing in ICT Mumbai, and these are my students. I must thank my distinguished professors of endowment. There were two of them which supported me as Vice Chancellor. I also am a J.C. Bose National Fellow. I must thank ONGC Energy Center. And we have in fact transferred now our dimethyl ether technology to Godavari Biorefinery just this week. So this is 104 PhDs, 112 granted patents, masters 125, 485 papers, and PDF 43. And so I was very happy to find my name in the physical chemistry ranking of Stanford as within 0.02% in the world, number 1 in India, and number 66 in the world. But this would not have been possible but for the contributions of my co-worker and the generous support which I've been receiving from industry for a number of years. Thank you very much.
Thank you, sir. It's a commendable the talk. I hope that all they enjoyed, especially I enjoyed. So since I also do something a little bit in this area. So anyway, it is the audience, if they have any question, over to Professor Lolit.
Yes, thank you very much, sir. Now is the question and answer section. So if there is any questions and answer, please type in the Q&A section that shall be taken up.
Meanwhile, if any of the panelists, if they like to ask anything.
From panelists, any of our want to interact with our expert, the Professor Yadav, sir.
Srivastava sir, would you like to say something?
Okay, then sir, shall I take up the few questions they have typed?
Yeah, no problem.
Thank you, sir.
Yes.
So, sir, one first question is that this hydrogen storage is a big issue in implementation. How to overcome this?
Yeah, very good question. You know, a
Yeah.
lot of work is being done in storing of hydrogen in the form of hydrides or, carbon nanotubes, surface modified materials,
Yes.
that is there. What are they talking about? So yes, hydrogen can be stored, and there are hydrogen-based cars now in Korea and California. They are doing it. That means that technology is available. At the same time, now the other realization is that carry hydrogen as ammonia. Of course, ammonia is highly corrosive, but can be carried, and they say ammonia-based cars will be also a future. But hydrogen-driven vehicles is not something which is beyond imagination. It is already happened. And I had some slides on hydrogen-driven cars in Korea and California and all. So they are already doing it, and they are safely done. Normally, what happens in the case of these kind of gases, because they require high pressure to store it, instead of storing them in a big cylinder, if you store them in small pipes, because the thickness of the pipes goes down. Okay, that is the beauty of the material. So you go down with pipes. So instead of one, you have several pipes in which, like, shell and tube type of heat exchangers where you store it and then you use it. And every now and then you have to refuel it. So maybe at least 200 kilometers it should go, and then the tank is refilled. And so that logistics, supposing we had this problem when the petrol was introduced, diesel was introduced, they had a problem at distribution. Then we had the product distribution of this LPG gas. Now we have natural gas going in pipelines, right? So when I say about dimethyl ether from carbon dioxide, that LPG network infrastructure can be used without any problem. LPG is a very good substitute for diesel and all. Hydrogen is, yes, there are issues related to the stores, but technologically they can be overcome. And a lot of work is being done. And with this International Hydrogen Council, which was established in 2017, say that it will grow like anything. Before we imagine by 2030, a lot of these international companies and nations will join their organization, because their whole objective is to, propagate hydrogen-based economy.
Yes, sir. You have nicely given the ideas for storing the hydrogen. Sir, the next question is coming from the DRDO. The question is, what are the future scope of MEC and the MFC, and what are their probable applications specifically in the defense?
What is that?
MFC, sir, microfuel cells.
Fuel cells.
Talking about MFC, how it is applicable.
You are talking about microfuel cells?
Right, sir.
Yeah, look, that will have tremendous impact in fuel cell industry. Is revolutionized because of hydrogen.
Sir, his question is particularly application towards the defense.
No, look, there are many things in defense which is secret technology, right? You can definitely use it. Like hydrogen can be used even in this by ISRO. ISRO definitely can use hydrogen, and it is one of the fuels, which is a lighter fuel. So once again, that technology is available. It is not that, but fuel cell technology is developing so rapidly that is what is generating as electricity and all. No? And fuel cell driven cars is a reality again.
Yes.
But sir, the problem with the large scale, the production with the MFC, still I think a lot of questions are there. So.
No, I would not say the problems have been solved. What I'm saying, there is a continuous development in that area.
Right. Yes, sir.
And a lot of people are filing patents. You do some
Right.
patent search and you will find a lot of people are filing patents. That means they have done.
Yes, yes, sir.
They may not reveal everything in the patent, but yes,
Right.
they are doing it.
Yes, sir. Yes, sir. So, yes.
One curious questions is coming from our students from our Mizoram is that what about the hydrocarbon in the Mizoram?
Oh, okay, you have hydrocarbons there. Look, I told you we have to have a combined mix for some time, and later on we have to forget about that hydrocarbon if it is going to pollute. That is, in my paper I argued that you for some time you can use that hydrocarbon because see everything boils down to economics. If something is not economical, you are not able to extract that oil by even using tertiary methods of oil recovery, then it is no good. Right, because that cost of oil will be very high. So ultimately, it is cost of production and its impact of economy that will decide. Believe me, even before you think, you may discontinue using this. So nowadays, what are they doing? They are talking about crude to chemicals, variable, fuel plus chemicals. So otherwise, earlier refinery means fuel. Now it is a lot of chemicals.
Yes.
The variable fuel chemical ratio is being planned. So that was the West Coast refinery, which Indian Oil, BPCL, HPCL, they had planned, no? In Maharashtra, in Ratnagiri. So that is what it is. So this is going to happen. Even Reliance has announced crude to chemicals.
Yes.
I think there are no more questions. Sir, from anything from our Vice Chancellor, sir?
Thank you, Lalit. I don't have any questions. I thank just only Professor Yadav for giving wonderful narration about the non-conventional energy and alternate energy sources. I thank you very much, sir, for
Thank
giving
you.
excellent lecture. Thank you, sir.
Thank you so much for inviting me. Divakarji, thank you so much.
Thank you, sir.
As
Sir,
usual, and I hope things become normal soon and I'll be able to visit your university
sir.
once again.
Sure, sir. We are thinking some kind of collaboration also through our center, and we
can
should
definitely
do something for the defense DRDO, sir.
Yeah, we can definitely do that. There is no issue. We can definitely do that. In fact, long time ago, actually, this was, maybe about 15 years ago, DRDO had approached us because they do a lot of nitrations and things like that. And I had visited their labs in Bhandara. I had gone and seen the factory. In fact, I had seen the DRDO lab in Pune also. Where they are, and there also they are doing nitration and chlorination, all those things I had seen. So we can definitely have a collaboration.
Sir, we should do through our center. So we should
why not? Why not? We can,
for the DRDO, we'll make a plan and then.
Look, I'm all for collaboration. My job now is what I wrote so many papers, got so many patents, produced so many PhD. Now my job is to transfer technology, which I am doing. That is what I want to do actually. Now I have no administrative load. I can do it.
Sir, Srivastava sir, DGTM sir, he mentioned that his network is very unstable. If it is stable, sir, can you say something, sir?
Last 5 minutes, I've been able to clearly hear. So it was very interesting talk and very worth listening and informative. We look forward to having some collaboration through our center in Mizoram University. We should work towards next generation fuels and what can be done for our defense forces. As Professor Tiwari said, let us work out some common interest program so that we can work together.
Yeah, we can sign a tripartite agreement between
sir.
DRDO, Mizoram, and ICT. We can do that.
Yes, sir. So now the question is to actually identify the problem so that
correct. Your top priority. You have to list that top priority, and then we can have student exchange. We can have all sorts of things. We can definitely do that. A joint for PhD program, development or postdoctoral fellowships, things like that. We can do it.
Yes, sir. So I'm actually indebted to you today because we hear so many talks, but many talks are not informative. Very informative, and it was worth spending 1.5 hours or whatever time we spent.
I'm
Because
sorry I exceeded my limit, but then I thought I should tell you the full story
no
because
problem. So it was very
yeah,
good.
yeah.
Actually, since I'm sitting on my table and my network also was unstable. I had
Oh,
to
I'm
take
so
some phone calls, which I regretted why I took.
I understand that. This is a issue nowadays. We are doing all online video course and lectures and all. Sometimes students say I did not listen to your lecture, so we are recording and they can revisit it. Things like that. So that is happening. But I'm very happy, Professor Tiwari. You called me. You remembered me. And you said I'm very happy to talk, and I hope I have given some new knowledge to the participants.
Yes, sir. We are thankful to the DRDO also, sir, for supporting us.
Yeah. No, that's what I complimented you in the very beginning for that.
Thank you, sir.
Yeah. Chalo. So
Sir,
I can.
shall we propose the vote of thanks, sir?
Yeah. Go ahead.
Okay.
Okay.
Thank you very much, sir. So now we come to the end of the first lecture series of the this Atmanirbhar Bharat, which is we have initiated with the Mizoram University and this DRDO, the Ministry of Defense, the first seminar, technical seminar series to commemorate the 75 years of independence. On the first topic is the Atmanirbhar Bharat in energy and the environment, net zero goal. Our honorable speaker, the Professor Ganpati D. Yadav, sir, the Padma Shri awardee from the ICT Mumbai. So he has been given a very informative information. As sir has mentioned, he has started taking class from 9:30, then 11:30, then now is the almost one. Continuously, sir, we feel very extremely sorry with the.
No.
Very tired.
Actually,
9:30,
yeah.
you keep on talking up to almost 1. Sir, you are highly energetic person. Thank you very much.
I had to stop my class because I told the student I took early. Normally I used to take from 12 to 1 or 10 to 1, but I said okay, I'll take before and I curtail that class because I had promised you 11:30.
Yes,
So
sir.
there is no problem. I have not taken even glass of water because I was engrossed in giving the talk.
Yes, sir. So that shows how much you have interested in your research and your sharing your technology, sharing your knowledge to the participant. You don't feel tiredness when you keep on saying that your knowledge, your experience to all the participants. So we all are benefited with your experiences. Hopefully in future also the guidance and your ideas will surely be able to bring some of the things for the theme which is related with the Atmanirbhar Bharat. So the self-reliance, so that we all can work together with our Mizoram University with your guidance and your suggestions. The things can be do further better. With this, I would like to thanks to the speaker again. Then next, I would like to thanks to our honorable Vice Chancellor. He is also in the transit. So he's traveling, but he has also listened to all the talks since from the beginning. Thank you very much, sir, Professor Sambasiva Rao, sir, the Honorable Vice Chancellor of Mizoram University, for his kind support and encouragement to conduct such activities in the Mizoram University. And at the same time, I would like to thank the DGTMs of the DRDO, the ISB Srivastava sir, for his continuously attending the seminar from the beginning till the end. Even maybe some network issues may be facing, but that shows the interest about your talk, sir. And we also like to thanks to the Dr. Pathak sir from the DRDO for their supports and the encouragement to conduct this seminars with the Atmanirbhar Bharat. Now, I also like to thanks to our ICT Center for support to conduct the webinars. The last but not least, all the participants from the DRDO and the Mizoram University and all across the India. Without your participation, this kind of the seminar has no meaning. So with your active participation and the very the useful questions which you have been raised about the storing about the hydrogens and all those things like that, and the applications with the defense and all those things, this will make more interesting to our speaker also. That shows your interest with this area, and then that gives the ideas how the things has been moving with the themes of the net zero goals, particularly for the energy and the environment. So we have to save both energy and the environment. What our today's speaker has highlighted very clearly from his expertise in the field, and sir has also give the ideas how they have developed in his laboratory and all those things like that. So if in future also the sir has also agreed to do any collaborative or any suggestions which he can be always give guidance to as sir has clearly said that now he has free from all the administrative load. So he's now time whatever he has gained in last many years to transfer his technologies ideas to the product to the application point of view. So that is the real things which are needed in this present era. So that has been highlighted. So with this, I would like to thanks to all the members who are in the panel list for valuable times and the suggestions which has been given from time to time. With this, with the permission of the Vice Chancellor, we would like to formally close the session.
Thank you.
Thank you.
Okay, sir. Thank you, sir. Thank you.
Allow me to leave. I have to go to my office now.
Sure, sir. Namaskar, sir.
Okay, now I can.
Thank you, everyone.
Okay, bye.
Thank you.